So what we need to do on these is, again, we're going to set them up. Okay? And the first one that we'll look at is question 3, and it is a simple joint variation question. Okay, so it's a simple joint variation. Let me turn this off real quick here. So we're looking at joint variation, or not joint variation, a direct variation on question 3. And what we're going to have to do is set up our formula. Right? And we use that to find our K. So let's look at question 3 here. So this one relates to Ohm's law. And it says, according to Ohm's law, electrical current, I, in amperes. Yep, do you need a homework packet? Yep. Okay. All right. Here. Anyone else need that homework packet? Gabriel, do you have the homework packet? Yep, I've got one here for you. And I did look up your address to get you that certificate. So after class, I'll show you what address is on file and we can change it. Okay? So I didn't forget, I got it right up here for you. Okay. So let's now look at question 3. So we're looking at Ohm's law, and it says varies directly. Now, when we talk about direct variation, what does direct variation mean? Direct variation means they multiply together. Inverse means what? Inverse means they divide. And what about joint? Joint means multiple variables. And they can either be multiplied or divided. Okay, so this is direct variation. So current I varies directly as the voltage V. So what's our formula look like? I varies directly as the voltage V, so that's going to be I equals KV. So that's our formula there. Now, what do we need to find? Well, we need to find that K. K is a constant. It could be something like pi. Pi is a constant like that, or gravity. Oh, thank you, Cody. And I'll get that graded for you. Probably, I'll probably have it graded tomorrow. Okay, so we're going to be looking here at this. We're going to be finding K. So we've got our formula set up. Now, what do we know? It says when the voltage applied, let's read it here, when 17 volts is applied, the current is 2 amperes. So what does that tell me? My voltage is 17. I is 2. Plug that into our formula. And we'll just simply finish it. Divide by 17. And so what's our K now? Well, K is going to be 2 over what? 17. So that's our constant. What's our formula look like? Looks like I equals 2 over 17 V. That's our formula. Now, what do we want? Okay, we need to make sure we answer the question. So we want, what is the current? It says, what is the current when 24 volts is applied? So we want to find the current. With 24 volts. So we're going to plug in 24 for the V. So now we have I equals 2 over 17 times 24. We can clean this up a bit. So that's 24 times 2. So that's 48 over 17. And I don't think that'll break down much. Nope, it won't. Or you could write this as, it says 2 decimal places, or you could write this as 2.82 amperes. So that's what we need there. So 2.82 amperes. We'll just divide them out, and it says round to 2 decimal places. So is everyone okay with that? That's direct variation. Direct variation means we multiply. So what do? We write up our formula, plug in the values that are provided, find k, and then find the missing part off of that. So this goes with question 3. Question 4. I believe question 4 is an inverse. So let's work with question 4. See if we can't see how this will work. Okay, so question 4. The weight of the body above the Earth's surface is inversely proportional. So inversely proportional, that means we're going to divide to the square of the distance. So that means we're going to be dividing by the square of the distance. What is the effect on the weight when the distance is multiplied by 4? So let's see what happens here. We're going to plug in some values and we're going to see what changes in our formula. So our original formula says the weight of the body above the surface of the Earth is inversely proportional to the square of the distance. So that means your weight is equal to some value of k over the distance squared, right? That's our formula. Now, we really can't find k because k is going to be an unknown and we don't have enough information to work with it. But what does it say? It says when the distance is multiplied by 4. So we're going to multiply this distance by 4. So let's work with 2 of these and see how they relate to each other. Let's start off by working with the distance. So let's let the distance equal 1. What would my weight be if my distance equals 1? Well, that would be k over 1 squared, and that would come out to be k, right? Now, what are we going to try to do? We're going to try to multiply that distance by what? 4, okay? So, if we start with a distance of 1, multiply it by 4, that means we're going to use a distance of 4. Now, if I plug in a distance of 4, right? This one's with a distance of 1, and that came out to be k. Let's try it with a distance of 4. 4 squared, right? And 4 squared is what? 16. So look at how these compare. When I multiplied it by a distance of 4, what happened to my weight? It went down to 1/16, right? Went down by 1/16. Because this one was k. When we multiplied it by a factor of 4, right, it actually got divided by 16. So the weight is divided, if I can write it right here, by 16 when the distance is increased by a factor of 4. So we can see here. So why is it increased? Why is it divided by 16 when the distance is increased by a factor of 4? Because we're not just dividing by that distance, right? We're dividing by that distance what? Squared. So if you increase it by a factor of 4 for the distance, the weight will go down by 16, by divided by 16. Right? And why is it 16? Because 4 squared is what? 16. This is how I checked it. So I used 1, I plugged it in, and I got k. 1's a good place to start. So we want to multiply that distance by 4. Well, 1 times 4 gives you 4. When you plug it into your formula, what happens? It's not just divided by 4, it's going to be divided by 16, because 4 squared is what? 16. That's why the weight is divided by 16 when the distance is increased by a factor of 4. It's divided by the square, not just by itself. If it was just inversely proportional or inversely varied, then it would just be 4 and 4. But in this case, it's not. It's going by the square. Does that make sense on that? A little bit? You just want to see that the squared makes a big difference. Question 9. This one's going to be a joint variation question, and we have lots of variables going together. When we talk about joint variation, that just means several things go together. So we're looking at the volume of wood in a tree. And the volume of wood in a tree varies jointly. Now that just means we have multiple variables. That's all that means. Varies jointly as the height of the tree and the square of the distance around the trunk. So what's our formula going to look like? Now, I like to use words. You can use variables. So we know our volume is going to equal k. That's our unknown factor. And it varies jointly as the height of the tree. So that's going to be the height here. And square of the distance. All right, how I set that up. So we've got the height of the tree. The first part is what you want. So volume is this. We want the volume. Varies jointly. Jointly just means we have multiple parts. As the height of the tree, so there's our height, and the square of the distance around the tree trunk. So that's that piece. Now, we're going to fill it in. So what do we know? We've got to find our k. So our volume that we're going to be using is 15.84. K again is the unknown part. The height is 22. And the distance around the trunk is 3 feet. So that's 3. And then we have to square it. So let's see what we're working with here. So all the pieces get plugged in. And we'll just multiply quickly here. We've got 22. 3 squared is 9. 22 times 9, that's 198. So 198k equals 15.84. And we'll divide by our 198. So 15.84, we're going to divide that by 198. And that comes out to be k equaling now 0.08. Now, what might k represent? Well, k might represent the type of tree. Some trees are denser than others, have a higher volume. So this might be maybe a maple tree. Maybe a walnut tree would have a different k. That's what k is. It's specific to something. So when we talk about gravity, okay, there's a different k for gravity on Earth versus gravity on the moon. They're different. Okay, so they have a different k value. Same thing for different cars and their braking. They have a different k because one car might be heavier than the other car, and that would change your k. So we have this k, so what's our formula look like? Our formula is the volume equals our k, which is 0.08, times the height times the distance squared. Now we can fill it in. So what are we going to fill it in with? Well, let's see. Let's put this up here so we can see what we've got. We've got our formula, and it says, what is the volume obtained from a tree that is 36 feet tall, having a measurement of 4 feet around? So we plug our values in. And that's going to be 0.08 times that height, which is, in this case, 36, times that 4 feet around, and that's squared. We'll go ahead now and multiply these together. Don't forget you got to square that 4. So 0.08, we'll multiply that by 36, multiply that by your 4 squared, which is 16, and that gives you 46.08, and we need to make sure that we label it. Now, these are going to be in feet. This is a volume, so when we talk about volumes, it's in cubic units. So it would have a volume of 46.08 cubic feet. So make sure you label them. Is everyone all right with that one? So that's what you should have gotten on that one. But do you see how I put the formulas together? I'll move it up so you can see the formulas here. But again, first things first, write up that formula, find your K. Once you found the K, you use that, plug in the pieces that they provided to get the missing part. And I know these can get confusing with all the words. That's why I like to write it out and not just use an H and a V, because then it gets confusing. So let's try 10. Leave that one up there so you can continue to copy it if you need to. Let's talk about question 10. So, the cost of stainless steel tubing varies jointly as the length and the diameter of the tubing. So, jointly, that means we do 2 pieces here or more, and it is jointly as the length and the diameter. So, what are we looking at? We are looking at the cost. So let's come up with our formula. The cost now is going to be K. There's always a constant K we have to find. And it varies jointly as the length and the diameter. So these get multiplied together. So that's what we've got there. Now, what do we know about the cost? Well, it says a 5-foot length with a diameter of 2 inches, it costs $48. So it costs $48 for that tubing. We need to find our K. Now, the length of that tubing is 5 feet. Diameter of that tubing is 2 inches. So we'll go ahead and just multiply these together. This one's actually pretty easy. Multiplying them together, you get 10K equals that 48. We'll divide by our 10. And these you can rewrite, since it comes out nicely, as a decimal. And that's going to be a K value of 48. Or sorry, of 4.8. Right? So that's our K. Now, rewrite your formula. Cost equals 4.8 times the length times the distance. Plug in your new values. What do we want? Well, we want to know how much will a 9-foot length of pipe with a 3-inch diameter cost. So 9 foot is the length. Diameter is that 3 inches. So we'll plug those in. What is my cost going to be? So that's what we're looking at. I'll write it up. I'll put it up here so we can see it. want to see how much it will be for a 9-foot length, 3 inches in diameter. We want the cost. And it says round to the nearest cent. So we'll just multiply these together. 9 times 3 is that 27. Times that 4.8. That gives you now $129.60. So hopefully they're starting to make a little more sense. I know a lot of students struggle with these just because they're applications. That's the only reason. So it should come out to be about $129.60. That was 3-7, which was variation. Today we're going to be looking at 4-1, which is inverses. We're going to talk about what inverses are, and then we're going to find them. It's actually a pretty short section. So we're going to look at 4.1 here. Now, when we were talking earlier about functions and graphs, we had the vertical line test, right? And we drew vertical lines, and if any line touched the graph at more than one place, it was not a function. And you probably saw that in intermediate algebra. Now, in college algebra, we're going to look at inverses. And instead of a vertical line test, we're going to have the horizontal line test. And same as the vertical line test. What you're going to be doing is you're going to be drawing horizontal lines. Oh, yep, just a second here. I'll be right back. Just a moment ago, we were talking about the vertical line test that we used for functions. We did that in intermediate and college algebra. Now we're going to look at the horizontal line test. And for the horizontal line test, what you do is you draw horizontal lines. If any line touches the graph at more than one place, it is not one-to-one and has no inverse. We'll talk about what the inverse is here in a moment. So I'm going to give you some graphs, and you're going to tell me if this is one-to-one and if it has an inverse. So if your horizontal line touches the graph at more than one place, it is not one-to-one and it has no inverse. So I'm going to draw probably 3 pictures. We're going to talk about each one, and we're going to see if these are one-to-one. So are the graphs one-to-one? Start off with this one. Would this one be one-to-one? No. Why not? Okay. Just like we did with the vertical line test, we do a horizontal line test. This line touches the graph at 2 places, so this is not 1-to-1. So it's not going to be 1 to 1. Let's do another one. What about if it was only half of it? What about if your graph looked like this? Let's say if you only had half of it like that. Would that be 1 to 1? Yes, it would. Okay, right? Because this touches at only one spot, so this is 1 to 1. One more. And then we'll talk about how to find the inverses. Well, I'll have you graph one. How about I give you this function? How about f of x equals, how about 2x cubed minus 1? Let's see if this one has an inverse. Now, I think this one will. Why? What does a cube look like? Let's just do a quick refresher of our graphs. Remember, a cube function looks like that, doesn't it? And what is that minus 1 going to do? Move it down. And what is that 2? Well, that's a 2 over 1. So up 2 over 1. Okay, let's draw our graph and see if this one has an inverse. If it's 1 to 1. If it's 1 to 1, it has an inverse. So we're going to be starting at what? We're going to be starting at, we're not going left or right any, so that's going to be at 0, down 1. So we're going to be at 0, down 1 unit right there. And then what are we going to do? We're going to go up 1, 2, right? And over 1, make our dot, curve it together. What about the other direction? Go down 2, back 1, and you curve it here. Is this 1 to 1? I think it is. Why would this one be 1 to 1? 1 to 1 just means that it has an inverse. So this one is 1 to 1. So it is definitely 1 to 1. Now we're going to talk about how to find these inverses. So the first thing we need to learn about is what functions have an inverse. So we're going to start with that. Let's look back at our common graphs and see which of these functions has an inverse, just by looking at the graphs. So I'm going to put the column ones up here. F of x equals x. That's a line. It's called a linear function. Does this one have an inverse? Yes. What about f of x equals x squared? What about our squaring function? Does this one have an inverse? Yes or no? No, this one won't. What about the square root graph? Does that one have an inverse? I think square roots do. Because a square root would look like this. It passes the horizontal line test. So, yes, this one has an inverse. Inverse just means it's 1 to 1. 1 to 1 and inverse, they mean the same thing. What about x cubed? Okay, I think x cubed will work as well. So x cubed looks like this. And so an x cubed function, it also has an inverse. So far, what's the only one that doesn't have an inverse? X squared. There's another one that doesn't have an inverse. The absolute value. Why would the absolute value, bless you, not have an inverse? It wouldn't have an inverse because this does what? Fails the horizontal line test. So this one does not have an inverse. Now we're going to be finding inverses. So what we do when we find inverses is we have a step-by-step procedure. So we want to try to find the inverses, if it has one. What we do is step number one, when we find our inverse, okay, step number one, we check to see if it has an inverse. And what functions do not have inverses? These two do not have inverses. The absolute value of x and also what? X squared. So those do not have inverses. So if ours has a square in it, or also any even power, because it could be any even power, is going to behave like a square. So absolute value of x, x squared, or x to any even power is not going to have an inverse. So that's the first thing you do, is you check to see if it has an inverse. Step number two, you replace f of x with y. Step number three is you switch or swap out x and y. Step 4 is you solve for x, and then, oh, sorry, not x, solve for y here. Let me make it look right. Solve for y. And then what you do is then replace y with what's called f inverse of x. So first thing you do is you check to see if it even has an inverse. Now, some functions have inverses, some don't. These do not. Absolute value, x squared, or x to any even power. If you have that, then it automatically has no inverse. If it has no inverse, you're done. If it does have an inverse, then we're going to find it. So what we're going to do is we're going to make our f of x y, because f of x and y can be used interchangeably. And then we're going to swap out or switch out your x and your y. And then we're going to go ahead and we're going to solve that for the y again once you switch them. And then you're going to replace replace y with your f inverse of x. That minus 1, that said f inverse of x. So we'll do some easier ones to begin with. And then once we know how these work, then if we have time, I'll show you how to check to see if two functions are inverses. But let's work out some of these where we try to find them. So let's pick these from our textbook. And I can make them up as well. How about we look at, well, there's some from our textbook. Let's try to find one that's not too terribly difficult. I'll just make some up. Let's try to find one. Let's find the inverse. But I give you f of x equals 4x minus 7. Well, first off, does this have an inverse? Yes. Okay, it is going to have an inverse. So how do we find that inverse? Why does it have an inverse? It has an inverse because does it have any squares in it? No. Any absolute value? No. So it will have an inverse. So that's the first thing we do, is we always check to make sure that it has an inverse. This one does. Now, what do we do for our next step? So we check to see that it does in fact have an inverse. So for the next step, what we do is we replace that f of x with y. This, by the way, is a linear function. This is a line. And then what do we do from there? Now, next we're going to swap or interchange the x and y. So x becomes y becomes x. So we switch them around. So swap out your x and your y. That's all you need to do. And now we just solve it again. And this time we solve it for y. So I'm going to add my 7 over. Now we've got 4y equals, when I move it over, x plus 7. We'll divide by our 4. That gives me then y equals, when I resolved, x over 4, or 1/4 x plus 7/4. And we replace that y with your f inverse of x. So we can see here. Right? So there's our function. So how do we find if it's an inverse? We look at our function and we see, does it have an x squared in it? No. Absolute value? No. So we know it has an inverse. We then replace f of x with your y. We switch out or swap out your x and your y. So y becomes x becomes y. We take it and we resolve it. And that gives us our solution. Now, let's do another one. So that one was a pretty easy one, right? That one had an inverse, and we were able to find it. Let's do another one. Let's try to find the inverse of this one. Well, we know that this one does, in fact, have an inverse, right? How do we know that? No x squareds, no absolute values, none of that. So we're going to go ahead now and replace f of x with y, so we know it has an inverse. Then we're going to switch out x and y. So x becomes y becomes x. And now we need to solve it. So this one may take us a little bit of thinking about how to solve these. This is going to make us factor. So I'm going to write that as over 1. I'm going to cross multiply. That clears out my fractions. So that gives you x times y minus 7 equals 3. So I'm going to have to distribute my x through. And that's xy minus 7x equals 3. Right? So I'm just distributing through there. Nothing new. I'm going to go ahead now and I'm going to add my 7x over. And now we've got xy equals 7x plus 3. I'm going to divide both sides by my x. Okay. And what does that leave you with now? Well, that leaves you with y equals 7x plus 3 over x. And what's our final step here? Replace y with what? F inverse of x. Okay. Now, when we work these out, we also have to make sure that we consider the domain. What value is not in the domain? What can we not use for x? Well, we cannot use x equaling what? 0, because that would give you what? That would give you division by 0. And this one should have had x can't equal 7, because that would give you division by 0. Right? So we can't have division by 0. If you forget to write that out, that's okay. Main thing is we replace your f of x with your y. We interchanged or swapped out my x and my y. Then we cross multiply, distributed through. Move that 7x over. And then we divided by that x to get rid of it. So let's do another one. Let's try another one. Does this one have an inverse? Yes. So we know this one has an inverse. Why? It's cubed. Okay? Cube functions have an inverse. So what do? We want to find the inverse. We replace f of x with y. Now, we then interchange or swap out your x and your y. Now, we need to solve this for y. We covered these way back in chapter 1. What is the opposite of a cube? The opposite of a cube is a what? Cube root. So that's what we're going to be using. Okay? So I need to get the y by itself. First thing I'm going to do is I'm going to divide by that 4. That'll make it easier. Then we can use our cube root. So divide by our 4. So that leaves you now with y minus 9 quantity cubed equals x over 4. How do we get rid of a cube? What's the opposite of a cube? The opposite of a cube is a cube root. Now with cube roots, you don't have to have a plus or minus. It's only the square roots. So that's going to be our cube root there. What does that leave you with? Well, that leaves you now with y minus 9 equals the cube root of x over 4. And how do we finish it? Well, we need to get the y by itself. So we're going to add the 9 over. And now we've got y equals the cube root of x over 4 plus 9. And what's our last step? Last step is replace y with f inverse of x. There's that. What we did was we identified the fact that it has an inverse. And then we went and worked all the way out. And we found it. Let's do another one. How about we look at a square root? Now on the square root, I might restrict the domain. Because you cannot have, remember, negatives in your square root. So we're going to try to find the inverse. On this one, we've got a little side note here that x must be bigger than or equal to 4. Why? This is just a side note here. Why does x need to be bigger than or equal to 4? Well, if it's smaller than 4, if it's 3, 3 minus 4, that would be a minus 1, right? And what do we know about the square root of a negative number? That comes out to be what? Imaginary. We can't have that. So that's why we have to restrict the domain to have x greater than or equal to 4. So next, we're going to replace our y with f of x with the y. Now we're going to then switch them out. So x becomes y becomes x. So x now equals the square root of y minus 4 with y being greater than or equal to 4. Right? X and y become switched away. Now we can finish it. So now we can finish this out. How would we finish this out? Well, how do we get rid of a square root? How do we get rid of a square root? We have to what? Square. So we're going to square both sides. And what does that leave you with when you square both sides? Well, that leaves you now with x squared equals y minus 4, right? We need to go ahead and solve this for 4. So we'll add our 4 to both sides. And that now leaves you with y equaling x squared plus 4. And rewriting that again, y becomes f inverse of x. So f inverse of x is now x squared plus 4. Now, we did replace your x and your y. And what do we know about our inverse? Okay, this is our inverse here. Okay. When we plugged in up here, right, we made sure that x was what? Bigger than 4. What about down here? What's the smallest it can be? Well, y needs to be bigger than 4, right? And if y is bigger than 4, your x also has to be, in this case, greater than 0. Why? Because I can't plug anything in and get this below 4. So this always has to be at least 4. So your x needs to be greater than 0. That way it works. So that's going to make sure then when you have a square there that your x is greater than or equal to 0. Because you can't have it go negative with the original square root. So that's the only thing you have to remember is when you work with these, that's going to change your domain around. What about this one? If I gave you this one's easier. Can you even do this one? No. This one has no inverse. Why does this one not have an inverse? Because it's squared, right? Now, you can have a square come out as the inverse, part of it, because it'll be a part of a square. Right? But if you've just got a square like this, it has no inverse, because it fails the horizontal line test. But it is this one could come out to be a square because your domain is restricted. Okay, your x can't be negative because that would force it to be negative under the root. Let's do another one. We'll do one more of these, and then we'll see how much time we have left. And then we'll talk about how to see if functions are actually inverses. So let's do one more. And I'll pick one that's similar to the homework here. Okay, how about something like this? Now, normally, this one would not have an inverse because of the square. But what did we say in this case? We said that x has to be what? Greater than or equal to 6. That restricts the domain, and so it has an inverse, because you're only looking at half of it. Because you can't make this go negative, and you've got to make x has got to be greater than or equal to 6. So this one does have an inverse, and we are going to try to find it. So how would we go about finding the inverse? So why does it have an inverse? Because of this, because you restricted your domain. If this wasn't here, if it didn't have this condition, then it wouldn't work. So this one does have an inverse. So what do? We replace f of x with y. And then our domain becomes our range. Now, what do we... Oh, sorry about that. Should still be an x here. Leave it as an x. And now we switch our x and our y out. So these get switched around. Right? That's all we're doing is switching around here. Domain here becomes your range. That's just what happens is the x and the y switch around. Now again, why does this one have an inverse, even though it has a square? Because your domain is restricted here. If you didn't have that restriction, see, then it would not have an inverse. So how do we find our inverse? Well, what do we first do? We square. Okay, so we're going to square both sides. That's going to then leave me with x squared equals, now when we square a negative, it becomes what? Positive. So when we square that negative gets squared, it becomes positive. And then we have y squared minus 36. Okay, so we need to rewrite this again. We're going to go ahead and add that 36 over. And we get y squared equals now x squared plus 36. And how do we now get rid of that square? What is the opposite of a square? Well, the opposite of a square is what? Square root. Now, normally when you take a square root, what happens with that? When you normally take a square root, you get a plus or minus, right? But we don't have that plus or minus. Why not? Well, we don't have that plus or minus because we restricted our domain. Because x has to be greater than or equal to what? 6. We flipped it all around. Y has to be bigger than 6. Okay, so when we took our square root, we can do that because we can take square root of a positive number. It still comes out to be a positive value. And that's going to then leave you with the square root of x squared plus 36. Okay, now, it's positive. And what do we know about our values here? Well, we need to make sure that no matter what, this is going to stay positive. So x has got to be greater than or equal to 0. The domain is a little bit tricky, but most of the time your domain will be x greater than or equal to 0. Because this one, we have a plus, so we don't have to worry about the minus. That's why we can say x is greater than or equal to 0. And why do we not have the plus or minus case? All right, we don't have the plus or minus case because you can't have that. That would make it not an inverse. So we just leave it as the plus case only. And basically, that's half of a circle is what it is. Let's do one more. And then we'll see how much time we have left. I'll just give you one more. And this one's like question 7. just different numbers. Now, the last one had an inverse, right? Does this one have an inverse, yes or no? No. Why would this one not have an inverse? Do we have a restriction on the domain? No. So this one has no inverse, right? So look at your homework here. I only gave you one, but look at question 7. Does question 7 have an inverse? No. So all you would need to write on question 7 is what? No inverse. But question 6, you're going to have to work it out. Notice it's very, very similar to what we did up here. Just different numbers is all, right? Instead of a 36, you have a 5. Now let's talk about two functions and why these are inverses. It goes back to the definition of function composition. And we'll just do one of these. I didn't give them any in your homework for you to do, but I do want to at least cover the definition. F and G are inverses if F composed with G of X equals X and G composed with F of X also equals X. So F and G are inverses if your composition becomes X on both directions. It has to work in both directions. Okay, so now we're going to see if these are inverses, and I'll just pick a couple of these, probably do 2 of them, from our textbook. So let's do 2 of these. We're on page 445, and we'll look at question 37. And we want to determine if these are inverses. Okay, well, if they are inverses, what should they do? When we compose these together, if we compose these together, then they should do what? They should come out to be X. If they come out to be X, then they are inverses. Okay, so let's go ahead now and see if these are inverses. And they should be, but we're going to check. We're going to take F composed with G of X. So that is F of G of X. So that's F. Now remember our compositions. We plug it in. 1/2 X minus 2. We're on our F function, so we write it out. We're going to plug in our 1/2 X minus 2. Because that's our X there. Remember how we do our compositions. I know it's been a while. Distribute that 2 through, and what do we get? We get X and 2 minus 2 times a minus 2. That makes it a minus 4 plus 4. What does that come out to give you? X. So see, these are inverses so far. We also have to check G composed with F of X. And G composed with F of X would be G of F of X. Okay. G went first this time, so that's G of 2x plus 4. G is 1/2, parentheses for your x, minus 2. Plug in your 2x plus 4. Distribute through. And that leaves you then with x plus 2 minus 2, which is then x. Now, what do we know? We know they are inverses if what? If both of them come out to be what? X. Do both of these come out to be x? Yes. So that means these are inverses. So these are going to be inverses. I'm going to now do one more, and I'll pass out the sign-in sheet. So this will be our last question. Pass out the sign-in sheet here. One more. Now that one was in, those two were inverses. I'm going to give you one now that is not an inverse. So the next two are not going to be inverses. Let me find one that's pretty easy to show that they are not inverses. How about question 40? So question 40, this will be our last question to look at. These should not be inverses. Because f of x equals, on question 40, minus 4x plus 2. And g of x equals 1/4. And it's a minus here. X minus 2. So we're going to check. F composed with g of x is f of g of x. And so we plug our values in. So that is f of minus 1/4 x minus 2. And then, okay, that's our g. We plugged it in. And then we have a minus 4 parentheses plus 2 here. Just plugging it in into here. And let's see why this doesn't work. Well, if I distribute through, negative and negative makes it positive, and 4 divided by 4 is 1. So that leaves you then with an x. So that piece is okay. 4 times a negative 2, that makes it negative 8. And negative 8 plus 2, well, that makes it negative 6, and that is not equal to x, right? It should be if they are inverses. So these are not equal to each other. So this is not an inverse. Why are they not inverses? Because if they are inverses, you compose them together, and you better get x equals x. So what's our homework now? Well, our homework for next class period is going to be do that 4.1. So you should be able to do them all. So work through homework 4.1, and you will do them all. Please make sure you sign the sign-in.